intro. So yeah, I'll be talking about a small project I did to reverse engineer a keyboard backlight on my laptop. So first I'll just give a small intro about myself. So I'm a software dev working at a startup called Dite. I got into cybersecurity by playing CTFs. I'm sure a lot of you got into it the same way. So I used to play with a team called CSI CTF, and now I play at Dite with DiteSec. And fun fact about DiteSec, it's our second time here. So we actually placed first in the CTF last time around. So really happy to be here again. You can reach out to me over here itself after my talk, or you can drop me a DM. I can also give you my mail ID as well. So cool, let's get started with the talk. So I've split the talk into 3 sections. So in the first section, I'll talk about how I reverse engineered a Windows service which interacts with the backlight on my laptop. The second chapter is about how that software sort of used system protocols to, do operations on my backlight. So, and the third part is how to re-implement this same functionality as a driver, right? So, and as a bonus, I'll also show you some new functionality I found on the backlight, which wasn't really possible in the first app, right, on Windows. So, yeah. So let's start with the first section. So before we start with the reverse engineering, I'll talk about what the app actually is. So this is my laptop. It's the same laptop I'm doing the talk on. It's an HP WMI 15. So it basically has 4 zones of backlights. What that means is you can't set the backlight on each individual key. It's only on groups of keys on the keyboard. It's a very common feature on many laptops. So if I were to mark out the zones, right, I have one over here, one here, and one here. And there's one on the right. It's not showing on this picture. It's cropped out, but yeah. So you can set the state of these zones at a really fast rate. So this can simulate patterns which show on your keyboard, sort of, right? And this can all be done through the software, which I'll show in a bit. And lastly, there's this hardware key to sort of toggle the backlight on and off. It's on like the function row right here. It's the F4 key, right? So talking about the software, so it's called HP WMI Light Studio. It's a Windows app. It's just for Windows. So it allows you to choose between these sort of presets on the app to, simulate what's showing on the backlight. And this is fully closed sourced. So there is 0 documentation about it. And one last point I would mention about this, which we'll sort of see on the next slide as well. So these, the animations only work on this application when you're booted into Windows. So if I'm not booted into Windows, it will just sort of show the last thing the backlight was showing, right? So this will be an important point we'll take advantage of later to sort of figure out what's happening, right? So yeah, so starting with how I reverse engineered it. So the first part of the process was really simple. It was figuring out where is this service located on my laptop, right? So I used a very simple approach. On Windows, you have this task manager. I'm sure all of you have used it at some point of time. So I opened up the application, and there was this Omen Gaming Hub executable that showed up there. And also another service which starts up on boot. It was called Light Studio Helper, right? So already we know this, since this service, like the Light Studio Helper, starts up on boot, it would be the service that sort of in the previous slide I mentioned makes the patterns come on boot, right? So that's, yeah. And one cool fact about Task Manager, you can actually see the path on your file system where the binary is located for a process. So I could very easily just get that from the GUI there, right? And the next step was, of course, opening this folder and seeing what's inside it. So let me just close that, yeah. So I saw many DLL files inside this. So I hadn't done any Windows software in the past, so I didn't know which language I was dealing with at the beginning. So there was this Newtonsoft JSON DLL I saw. So if you have worked with C# in the past, you would know this is a very popular library to parse JSON strings, right? So that is how I knew I was dealing with a C# application. So I started looking for apps to sort of reverse engineer like a C# app. So I landed on this tool. It's called ILSpy. So I'll actually show a short live demo of how I reverse engineer it, because C# applications are fairly simple to reverse engineer. In this case, HP actually didn't really make it very hard to reverse engineer their application, so they had all that build symbols still in the binary. What that means is I could see variable names and method names as they wrote it in their source code. And that is actually a crucial point, because a lot of your time in reverse engineering actually ends up in checking each function path because you don't know what a function is doing. But if you know its name, you can sort of guess what it's doing and not go into paths which you know won't matter, right? So yeah, I'll open ILSpy up. So yeah, I've already loaded up the folder I showed you. I didn't do some more steps. It was basically just only loading in the folder into the application. I won't go into the entire process, but basically I found this package inside the software, which was called Omen 4-zone lighting. So you can see we have a class here, and it defines sort of many random constants, and each of these constants seems to talk about some operation you can do on the backlight, right? So I have one to get the state of each zone, what it's showing right now. I can set the state of each zone. I can set brightness. And these are all assigned an integer. And there's also this big integer, which we don't know what it does yet, but we'll see that in a bit. And then we have methods which basically use these constants to call some kind of a function, which I'm guessing interacts with the backlight, right? So there's this execute function, which is using those integers we just saw. So, for example, here's is lighting supported, and here's set brightness. So it's sort of passing the first integer as the same value every time, and then it's passing what operation you're doing and some kind of more things about data you can pass into the execute function. So like, let's say for brightness, I can control what's the brightness of each zone as a 4-element array, right? So that's passed in, and I can also get return data out of this function. So that's what I noticed, that everywhere in the code, they use this single execute function. So that's what told me that, okay, this is the only function I need to look at. And I can sort of ignore the rest of the code. So going on the execute function, I saw this mysterious reference to this thing called a management object. I had no idea what this is, so we'll see this in the next slides. And it was passing in some strings to reference, I'm guessing, something else on this laptop. And what it basically does after that is it takes the things you passed and dumps them in this management object and invokes some sort of a method, right? I'll go back to my slides so you can see this better. So yeah, this is the same function, and I've highlighted the important parts about it. So yeah, we're creating a management object, don't know what that is yet. So, and we're passing it some arguments, right? And we invoke a method somewhere here. Cool, that's the first chapter. So to summarize, we used ILSpy to basically reverse engineer .NET Windows service, and we figured out how this Light Studio Helper service works to a certain extent. We found these mysterious references to Windows APIs. So there was a management object, there was ACPI something, right? Cool, and there was some constant integers sort of in the code which signified what operation you're doing on the backlight. For example, check if the backlight is on or off, etc. Cool. So let's start with the second part of the talk. So I sort of went on like, so I tried to analyze more what those mysterious objects we saw previously mean. So I figured out we are talking about two protocols, ACPI and WMI. So I'll go over what these mean first, and then I'll also show you what they mean in the context of my laptop specifically. right? So before I talk about ACPI, I'll give a history of how I/O platforms usually work. So an I/O platform is basically, you can think of it like a mouse or a keyboard which is joined to your laptop, right? Anything that either takes input or you can show something on it, that's an I/O platform. It could also be a sensor on your laptop. So a thing about these I/O platforms is they need to tell your CPU about stuff that happened on them, right? So, for example, in the case of a keyboard, I need to inform the CPU when a key is pressed, right? So, yeah, so how that happened in the past, so this is a diagram of a really old CPU called the 8086. I'm sure some of you might have learned it in your micro course before, if you did take a micro course. Yeah, so how it worked was the I/O platform could send a pulse on this interrupt pin that's right here. Yeah, so and once you do this, you could pass an interrupt number to your CPU, which signified what kind of an event it was. So let's say in the case of a keyboard, it could signify a key press event, right? Or a event when you leave the key, right? So, and yeah, that's how an interrupt worked. And when the CPU got this, it would sort of execute another handler to serve that interrupt, right? And as soon as it was done serving that interrupt, it would go back to doing what it was doing. So it's called an interrupt because you're interrupting the CPU, right? So yeah, and the disadvantage of this approach, at least now, maybe not at that point of time, was there was no standard to sort of maintain these interrupt numbers for each I/O platform. In the when the 8086 was made, there were very less operating system standards emerging. So the people making the chip were the same people writing the software for the chip in many cases, right? So all of these interrupt numbers were fixed, and there was this need to control these sort of I/O platforms outside your BIOS firmware. So that's why we had this standard called ACPI sort of setup. So ACPI is built for exactly that, to move these I/O API interfaces out of your BIOS to your operating system, right? So how it did this is it introduced this new language called ACPI Machine Language Bytecode, which was interpreted and executed on your operating system, right? But where it was stored was still on your BIOS chip. So it was built by a manufacturer, it was hard-coded on the chip, and then there was this process where when you boot your operating system, it's loaded into your RAM. So I've built a small diagram for this. So there's this BIOS firmware on your laptop. I've just drawn a box for it. When you boot your laptop, it copies this ACPI data into your RAM, and this is basically a picture of how your RAM can look like. So the bottom section is the actual memory used by applications, but the ACPI data has its own sort of segment in the RAM where it's stored. It's a fixed location, right? And the operating system, after it has booted up, can then read this code from the RAM, right? So I can actually show you on my laptop how this RAM segmentation sort of looks like. So you can run dmessage to, yeah, so you can see on boot, Linux actually prints out the sort of address of each segment in RAM. So you can see one of these segments is reserved for this ACPI segment. So basically that's where this bytecode is being stored, and we have the other actual usable part of memory below, right? So yeah, and you can actually read this AML code on your system. So Intel has built this tool called IASL to basically reverse engineer this bytecode and read the actual ACPI language code on this. So, and Linux actually has an ACPI driver. It's shipped with most laptops, which mounts all this ACPI data into a fixed path. So I actually used this tool to reverse engineer what was in that path, and I sort of got like a big file out which was thousands of lines, and it represented each I/O platform inside my laptop, right? So we don't need to go into the syntax of this AML code, but basically you can sort of define these IO platforms, and you can set attributes on them. So we have like these unique IDs for each thing, and we can also have methods which do operations on these IO platforms. So yeah, and the next protocol was called Windows Management Instrumentation. So this was initially built as a protocol to sort of help sysadmins manage Windows PCs on a LAN, right? You could execute scripts on these, to maybe shut down the machine or boot it up or to retrieve some information. But what it is basically, it can do much more. So it's basically this API server that runs on your PC on boot again. So it's running on user space. And you can send API requests on this. So it's kind of listening on a port, right? And what it does is it will route your request to a service either on your PC or some other PC to serve this request, and it can do the operation there and pass back a response. So you can think of this like what microservice is in the context of cloud. It is sort of in the context of your own laptop, right? So the service could exist on your own laptop or some other machine. In the context of the stock, it will be about only my laptop. And there's this Explorer tool you can use to sort of contact the API server and get the list of actions and calls you can make on these services. So if you remember before, there was a reference in the strings to this class called HPQBIntM. So I found this on the Explorer, and each class on this API server has a unique GUID assigned for it. So I was able to get that out from my Windows OS, basically using this Explorer tool. Yeah, and now how it all links, basically. So Microsoft has built like their own extension for the ACPI spec. So this allows you to expose ACPI methods, which are on your firmware. They execute on the operating system, but they're read from the firmware. So as in your user space using this Windows Management Instrumentation protocol, right? So, and all you have to do is, so the manufacturer of your laptop, when he puts that AML bytecode on your laptop, he has to define a special IO platform in that. It has to have a fixed ID. It's called PNP0C14. So this is actually, again, a segment from the ACPI code in my laptop. So I found there was this HID PNP0C14 thing. And the next thing the manufacturer has to put inside it is this array sort of bytes, right? So these specify the bindings between the Windows management methods to the ACPI functions in the code. So what that means is I can call a Windows management function from user space, and that will be linked to an ACPI function on my laptop, right? And there's this tool you can use to parse the bytes I just showed you, WMI dump. So I can just pass it those bytes. It's a CLI tool, and it will show me these mappings, such as this GUID, which we saw on the Explorer window as well, is linked to this ACPI method AA, right? And here's the actual method. So this is the method in the ACPI code which is dealing with the backlight. The reason it looks so small is because it's calling another function somewhere else, which is really big. So we don't need to go into depth in how the ACPI part works, but yeah. This is just an overview of what I showed you. We can sort of skip this slide, but to summarize again, you can send basically API request to your API server, the Windows Management API server, and this will be routed using the specification I just showed you. It will be mapped to an ACPI function, which will do an operation on your backlight in this case, right? So yeah, that's the chapter 2. So a summary. So basically, we learned about two protocols. ACPI basically specifies this AML code. You can load, it is loaded from your chip into main memory, and you can use this to interact with IO platforms. WMI is just a sort of server to route these user space requests. And lastly, there's a specification which links both of these. So our plan right now to re-implement this as a kernel driver is simple. We need to figure out a way to implement these protocols there, right? So yeah, that's the third chapter of the talk. So actually, it's not that hard to implement this on the as a driver. So there is this method in this library called ACPI.h. It's already made because these protocols are so common, called WMI evaluate method. So we can actually pass this all of the information we got from seeing the application on Windows, like the GUID from the Explorer window, for example, that's right here. And we had those integers which specified operations. You can actually pass that here and add the actual input data. So you can pass all of this information to this method. It's already there in this ACPI.h library, which you can use in a kernel driver to basically call this function. So what I did was, my plan was simple then, to basically figure out how I can build a kernel driver to use this method in the right way. One thing about how you interface a kernel API from a user space. So in Linux, so you basically everything happens in terms of files, right? So there's this file system called sysfs. So all the subfolders and inside /sys very likely represent a kernel driver. So when you write or read to a file inside /sys, it's going to invoke a method in a driver somewhere. Very likely. It's not always true, but most of the times, right? So we need to define a file for our backlight inside this sys file system, right? So in my case, Linux has a standard for this sort of, unlike Windows where it was obscure Windows APIs. So you can define a file inside /sys/class/LEDs to represent your backlight. So in my case, I named this HP WMI keyboard backlight. And I also made a custom file to sort of represent the state of each zone, right? So yeah, this is the code for doing it. It's not important, but basically the important points are we can specify the name of the file, and also we have to define handlers for what happens when you read and write on these files, right? Yeah, and this is what the new, basically the files on my system look like. So I can basically look at the files inside this HP WMI keyboard backlight folder. So there's the important files are, there's this brightness file, which I have to handle to sort of set the brightness on my backlight. And there's this zone file, which I can use to set what shows on each zone, right? So in the next slide, we'll see how we write handlers for this zone file. So yeah, you can do that on your driver very easily. So in this case, we are reusing that function we saw in ACPI.h to sort of make the ACPI call to interact with the backlight. So we are using the information we got when we saw the WMI application, right? So we had this big integer there, and we had those small integers for each operation you can do on the backlight. So I passed these to these methods, and these will basically make those ACPI calls, right? So in this case, for the zone, I'm basically reading the state of what the zone is showing right now. And then I get that data and I sort of override the new state of the zone on top of it. And then I do another ACPI call to write on the zone again, right? And that's happening here. So yeah, that's how you set the zone things. And for the brightness control, this was actually really interesting. So on the Windows side, when I got this laptop, it only had two states of brightness, so either on or off, right? So you can't have a middle state. And this was sort of like a feature I did not like, because in the night when your laptop is really bright, like you want it to be a bit lesser. So yeah, so the first implementation I made for this method was simple. I did the same approach where it has only two states, where the light can be either on or off, and it passes like a fixed integer, like we saw in the reverse engineering side, and then it makes the ACPI call as general. But I figured out there's a trick you can do, so a bonus trick. So basically in an LED, when you pass a hex code of 0, let's say RGB value 0, right? It has to show black, right? Because that's black. But there's no such thing as black light. It just turns off, right? So basically, 0 is sort of lowest brightness, and the highest brightness is the highest hex value you can give, if it is white, right? So what you can do is on your driver, you can basically use this to implement brightness. So you can get the state of the zone at some point of time and just scale it by a fraction of the brightness value and to sort of simulate brightness, right? So that's what I did in the driver, which was actually, it should have been possible on Windows, but now it's actually there in this driver as well. So yeah, I'll give a short demo of how this works. So yeah. I'll just set up like a video stream to show up the laptop. And meanwhile, I'll also, So meanwhile, I'll just show you how the sysfs file system looks on my laptop. So I've already loaded in the driver I wrote. Yep. You can just leave it here. So yeah, so we had sys/class/LEDs/HP keyboard backlight. Yeah, this is the same file system tree I showed you in the previous slide. So first of all, we had this brightness file. I'll actually switch to root because some of these files need access, right? So, okay. So I can cat what's in this file first, right? So I can read the brightness sort of my backlight, and that will call a method on my driver, right? So yeah, and right now it's off. So if I basically now link this up, yeah, so the backlight is off. I don't know if you can see that. So I'll just make this a bit darker. Yeah. So yeah, and let's say I want to write into this file. So I can basically write the byte 1 on this, right? So if I do that, you can see it turns on. Right now it's showing animations because I have a script running on the background, which is sort of setting the state of the zone. I'll just stop that. Right. So you see it's static again. And oh, okay. Yeah, so it's on now. Right. And yeah, if I basically, sorry, just give me a second. Yeah, this will be easier. So yeah, if I echo 0 in, it will turn off, right? So that's the brightness control, and I can also set the state of each zone. So let's say I want to. So yeah, one thing about this I should mention is how I built the format for the zones is you can just pass the hex values as bytes for each zone. So we can use a tool to sort of read this using XXT, because if I use cat, it'll just print out random bytes, which won't make sense, right? Yeah, thank you. So yeah, this is the zone. So right now you can see the state of the zones right now. So there are some random hex values, and I can write into this file. I'll just turn it on so you can see that. So let's say I want to write all white in all zones. So that's basically the same byte everywhere. You can see it turns white, right? And I can also set individual zones. So that's the script I just was running on the background. It's a simple Python script to basically has like a while true loop which writes on this file at a really fast rate. So yeah, if I run that, yeah, it just sets the lights at a really fast rate. So yeah, that's how that works as a driver. And cool, yeah, and that's my presentation. Thank you. If you have any questions, you can reach out to me right now or later as well. Yeah.
Does anyone have any questions?
Hi, Rishit. Great presentation.
Hi, thank you.
Just want to know, you mentioned something about NewtonSoft.dll. You used it at some point. How was the interfacing important for the ACPI and AML modules for that? And why was it not directly from Windows itself that you had to move to Linux? Was it just because of the drivers and the file system?
So NewtonSoft, so in the context of reverse engineering the application, it sort of wasn't used here. I just used that to find out that it was using C# because I had no idea. So I just searched up what that library was online, and I figured out it was a C# library. That helped me figure out, okay, so I have to search for tools to reverse engineer C#, right? Though, yeah, it would be using this library, but only on the Windows side. So I guess what they might be using it for is they had these JSON sort of config files for models of laptops. So like the same software can handle multiple models of laptops. So, and they have different classes which those route to. So the JSON files were basically storing these mappings. I didn't show that because I wanted to sort of only talk about my laptop in this. So, yeah.
Okay, thank you, Rishit, for such an insightful session.
Yep,
Please give him a huge round of applause.